Hello, welcome to Curry Girl Tech Talk. I am Crystal Curry. Thank you for joining us. Today begins our 6-part series about artificial intelligence, or popularly known by the acronym AI. Have you ever wondered what artificial intelligence really means? Where did we get that term? And what does machine learning actually involve? Well, we are going to answer those questions. And my hope is that throughout this series, you will be enlightened and equipped with tools to empower your lives. In today's episode, we are starting with the historical context of artificial intelligence. Where did it begin? How did it evolve into what it is today? And what are the key concepts and foundational principles? Our guest today, Dr. David Lowry, is going to help us with these questions. How did you come across machine learning?
Well, for me, it was quite a journey that started in the late 80s, actually, when most people probably weren't familiar with machine learning. The term wasn't really very popular back then. But I think with my first encounter and so many encounters of machine learning, it really normally starts with having an issue or problem to solve. The value of machine learning is dealing with actually a very wide range of what would otherwise be challenging problems. So for me, it will make sense if I first set the scene. So in 1985, there was the discovery of the ozone hole. There was another British gentleman who worked at the British Antarctic Survey in Cambridge. At that time, I was just about to become a graduate student in Cambridge, and he discovered the ozone hole. So the task I was given as a student was to write the world's first 3-dimensional model for ozone depletion. So what we used
Sounds like a difficult task.
Well, it sounds harder than it is. What I used was a weather forecasting model, because you can think about it, for the chemicals in the air, they can either react with each other, or they can get blown around, or if they happen to be soluble in water, they can get rained out. So a weather forecasting model is a perfect place to describe this. I set about to write my model. It took me about 2 years. And when I finished, I wanted to know how good it was. And so I developed this voracious appetite for all the data I could. But to understand that data, it's helpful to set the scene. Like the ozone hole itself forms in a very specific situation. It's the polar vortex. I needed to get the data on this ozone and the other chemicals in the atmosphere to compare to my model. See, I could run my model, but maybe it's giving me a whole load of junk. So to know whether it's good or not, I needed to compare to observations. Yeah, so at this point, I'm not using machine learning. I then started getting together all the data I could from multiple satellites. And the reason this became a little challenging is these observations were being made in a dynamically evolving situation. When you come and look at observations from the satellites, you see a couple of plots there from 2 different satellites for the same situation, measuring the ozone at different resolutions. To my dismay, I was finding different instruments that were observing at the same time actually were biased relative to each other. And this was not just a one-off. Pretty much any set of observations I came across, for the same time, there were these biases. They were persistent biases. And what's more is they were actually not constant. They would be changing with location and time. So first I had to find out, how can I correct these biases? So that's what set me on this quest to find an approach that could do that. And quite by chance, I'm really, really grateful, I came across one type of machine learning that was available then called neural networks. So this was one. So the question now I was faced with, it's pretty obvious, what can I do about this bias? That's where the whole machine learning came in, because I didn't have from first principles a theoretical explanation. That's probably a good starting point. We use machine learning in many cases where we don't have a perfect theory. We have a lot of observations maybe of different parts of our system that might be all coupled, but we don't necessarily have a theory that neatly ties all the pieces together. Because if we did, we would use it.
So all of this data is helping you to form your hypothesis and validate all of the data that you've gathered to this point.
At this point, my problem was the data I was getting was biased. And before I could test my theoretical model, I had to get rid of these biases. This ozone depletion, it involved several aspects. Part of it was the observation of ozone, and another part was the observation of the reactive chemicals. And the number of observations for those were very limited. So we had these global models like the one I had written, and the observations we did have were biased relative to each other, say for ozone. So what I really wanted in this equation is to estimate CLY, which was the total amount of this reactive chlorine, but that was composed of these individual components. And some of these, like HCl, hydrogen chloride, that was observed by the most number of satellites. But even the observations for that were biased relative to each other, and many of the other components weren't observed at all. I wanted to use machine learning to do two tricky issues for me. The first one was to correct these ubiquitous inter-instrument biases. And the second, could I infer the total reactive chlorine from just a subset of the components like this hydrogen chloride? We're comparing a pair of these satellites. Now, if they didn't have a bias, these would lie on a straight line. So satellite A sees a value, satellite B sees it, but we weren't seeing that. So if you notice, it's not even a straight line. We have this wiggly line. So what that means, the biases were spatially changing. So if I then use the machine learning, as you can see on the right, I'd straighten out this wiggly line. To my delight, I had found a systematic approach where for any pair of instruments, A and B, I could calibrate A as if it was B or B as if it was A, so I can put them all on the same scale.
Now, let me ask you a question, Dr. Laurie. How did the data that was actually collected from the multiple satellites, do you then analyze that data to get rid of those biases?
The machine learning did the cross-calibration. Without the machine learning, I got the data from the different satellites, but they weren't agreeing with each other. So it's like you put everything on the same scale, you like calibrate. And it turned out this was useful then for a whole set of other tasks. In the human body, we have lots of neurons, and that was the inspiration for these algorithms, where we have lots of inputs, some outputs that we can then use. So in this case, one of the inputs would be the satellite measurements from one satellite, and our output would be the satellite measurements from the other satellite. And the other inputs would be our context, like where we were horizontally, vertically, time of year, and so on. And what we always do when we have a calibration like this is we take a completely independent set of data that didn't go into our training, because machine learning learns by example. Mm-hmm. So to check, did we really learn, or are we just kidding ourselves that we've straightened this out? We take completely independent data we've never seen before, we plug it in and see, can we produce the known? So instead of just having 2 points to benchmark, we now have a continuous time series with an uncertainty estimate. So that was really big deal for me anyway. So what is machine learning? So there's a really quite helpful definition, but the simple idea is it's an automated approach to build a descriptive empirical model. So that's not theoretical. We just base it on the data alone. This gentleman, Arthur Samuel, he actually coined this definition in 1959. So that's a long time ago. And so he said, machine learning gives computers the ability to learn without being explicitly programmed. So what's exciting is machine learning, we're actually beginning to let computers learn by example to do a whole range of different tasks.
I think this is great, Dr. Lard, because I think a lot of people don't understand. They think that machine learning is a relatively new concept because of ChatGPT and some of the more popular implementations of what we call artificial intelligence today. But this gives us a really good history of where it actually began. Dr. Laurie is correct in that Arthur Samuel coined the term machine learning in 1959. There is a conference held at Dartmouth where John McCarthy coined the term artificial intelligence. This conference is considered to be the founding event of artificial intelligence as a field, with machine learning being a component of it. McCarthy was a cognitive scientist and computer scientist. You will see some even argue that conceptually, machine learning and artificial intelligence predates these guys. And in the early days of science fiction, humans have pondered ways of incorporating machines into human life for quite some time. So I think it's helpful to interject right here to let the audience know what a neural network is. A neural network is a machine learning program or a model that makes decisions in a similar manner to the human brain by using processes that mimic the way biological neurons work together to identify things, weigh options, and arrive at conclusions. A less fancy way of saying it is these machine learning models or neural network models are designed just like the human brain. For instance, if you remember when we were younger, we learned the alphabet, and then we progressed to learning how to form sentences. That's the same way that these neural network machine learning programs operate. They are given subsets of training data to learn, and it improved its accuracy over time.
That's pretty cool. Now, with a whole large language models, that really started in about 2017. That's a whole nother layer of it. Right. But there's quite a long heritage to these things before the very recent explosion, if you like.
And thank you for that, because I know that a lot of people think that it's new. When I look at this, I just think, wow, look how far we've come, and it's just exploding now, and how all the amazing things we're able to do at this point.
It's like standing, as they say, on the shoulders of giants.
Yeah, absolutely. Yes. And I do think, because I think back to some of the big tech, words that we use, and big data was one of them. And I think that did sort of pave the way for the larger, being able to aggregate large amounts of data, and how that synthesizing that data and all of that has contributed to us being able to further progress into more deep, what they call deep learning for machine learning.
Machine learning can be subdivided into two areas, supervised and unsupervised. So they sound really technical, but it's really saying a very simple thing. With supervised, we know what the answer should be. With unsupervised, we don't know what the answer should be. Mm-hmm. So an example of that would be, hey, I have this big pile of data, and I'm sure there's different regimes and zones or whatever we want to call it in there. And we're saying to the algorithm, hey, I have this pile of data, help me split it up into subpiles. So that each of these subpiles every member will be similar to the other members in the pile and distinct from the other ones. In supervised classification, we actually have a set of inputs and one or more outputs when we have examples of we know the inputs and the outputs. And for that, we try and do two types of things, a regression or a classification. In a regression, we're trying to estimate a real value, a number with a decimal point, significant figure. So in the example I was showing of calibrating satellite A against satellite B, that's what I was doing, a regression. So to do this, we always have two key ingredients. We have an algorithm that lets us do the learning. We can learn from a set of examples and do our task. And secondly, we have a set of examples, our training data set that we can learn from, algorithm and the examples. And for many of these tasks, there's multiple algorithms that are trying to achieve the same task by very different approaches. So, and a really important thing If we're doing a supervised learning, we always, and I'm going to say it again, always independently validate our data. We have to check this algorithm that's learned from these examples. If I feed it a set of examples that it never saw before, is it going to get the answer right? So that's the validation. We never want to use it without validation. One of the early examples often used in machine learning courses is of a guy called Fisher. And he was measuring irises, the width of their petals and the length of them and their sepals. And he wanted to use it to classify what type of irises they were. Now, the unsupervised classification is we now have no output. We've asked it the question, hey, I have this pile of data. Help me split it up.
Figure out the categories or figures.
Yes. One of the surprises maybe for me, and I think for anyone that comes to do machine learning, is how this is rather an iterative process. I'm trying to emphasize that it's like a jigsaw puzzle. So we're trying to study a system, but our information on that system could be coming from different places. Actually, 90%, maybe 99% of the effort for most machine learning problems is assembling our examples, our training data. And they could be coming from multiple places. So then we bring all this data together, we select our features, and then we give it to our algorithm, which learns from those examples. And then we want to independently validate how good is that doing. And then we create our model, we test it, and maybe we think we need to improve this. So we can iteratively go around this cycle several times.
Now, during this process, are you adjusting the data itself? The data itself remains consistent. It remains untouched. But the iterative process of once you've learned, then you adjust maybe the algorithm.
Sometimes that's becoming more and more automated now that we don't need to do it, but that's the lion's share. Now, for the algorithm itself, different types of algorithms will have different knobs and dials, if you like, that can be optimized. There's a process we normally go through called hyperparameter, these knobs and dials, optimization. So that tweaking and choosing optimal combinations based on how the model performs is invaluable. The two tweaks, if you like, we do are one, the feature selection, which can make a huge difference, and then the hyperparameter optimization. So we're not actually changing the data, just how we present it. And we're not really changing the algorithm, we're just tweaking the settings, like you could imagine your volume. Then for a regression, once we've finished with our model, we want to see how good it is. We've never used the algorithm without checking it. We do that with something called a scatter diagram that I've shown here. The observed against the estimated. And we want this straight line, 1-to-1. We don't always get it perfect like that, but that would be the optimal. And we then do it for our training data set, and then our independent validation. We hold back a random subset of the data that once we've created our model, we try it on. And we want that to perform just as well as our training data. There were many examples like this. So I showed you one for atmospheric chemistry, but there was another one used by the World Bank. The World Bank often use satellite data to determine, say, if there's a drought, when they're going to give financial aid to a country. They use these things called vegetation indices. It's basically the ratio of two wavelengths. Take your front yard. You go out, you look in your front yard. If it's just had a lot of rain, it's nice and green. But if it's been a dry summer, it's kind of maybe dried out, it's gone a bit yellow, and so on. So by eye, you use the level of greenness as a metric. Is your yard, the grass in your yard, under drought stress or not? So essentially, that's what we're doing here. We're using a ratio between two wavelengths. Then what we did is, again, use the machine learning, how to calibrate satellite A as satellite B, because when they set the thresholds for these indices, which determined whether they give food aid or not, they use the first satellite. But then every satellite has a life, and the next one comes along. And the next one, if it doesn't agree with the first one, now all their thresholds are wrong. So that you can see this is a common problem of having to do the calibration. We use wearable sensors.
Yeah.
So often, like I'm wearing this ring here that's measuring my temperature, heart rate variability, blood oxygen, sleep. So that's really useful. But we've used machine learning to go the next level and from our body's response to tell us about the air we've inhaled. When you or I look up at a light, our pupils shut down really quickly in a few milliseconds. We can actually film that. It's really cool. So we wondered, is that the only thing that our body responds to in our environment? And in fact, we were able to build the most accurate model to date where we could tell the exact light intensity based on our pupil diameter, and we could wavelength resolve this. We thought, well, could you do the same for the air we inhale? So, for example, many of us might have heard of the unenviable canary down a coal mine. When the miners would go down the coal mines, sometimes there could be hazardous gases and it could creep up on them. They wouldn't be aware of it. So they would take the poor canary with them. And the role of the canary was, if all the different birds they had readily to their disposal, it was the most sensitive to the environment. So if the poor canary conks out, it's time to go. So my mantra is, no canary has to die. So the idea was, supposing like in the science fiction movies, they have these suits and their suits are monitoring them. I wanted to know, could we get the composition of the air we are inhaling from just the body's response? And amazingly, the answer was yes. So from these parameters, like I mentioned, we can get from this ring, we can actually determine how many particles per cubic centimeter of a given size, like the COVID size, for example, that we're inhaling. And so we were doing this on the hyperlocal scale, the scale of you and me in walking around our rooms or neighborhoods. But we're also doing it on the planetary scale from the satellites. We also were doing it for robot teams, aerial robots, robotic boats, walking robots that could go into an environment and rapidly try and answer the question, is the area safe? If you can actually send robots with machine learning in to figure what the hazards are, then people don't have to go. But we're also doing the same thing 24/7 across neighborhoods. And so some of you may have heard of the illegal dump in South Dallas called Shingle Mountain. Folks in that neighborhood reached out to us, asked us to build sensors, and then we were glad to build them and provide for them, and that led to the closing of these illegal dump that was there. And so we use machine learning for the calibration of those sensors. Just like we had satellite A against satellite B, we can now calibrate cheap sensors against reference ones so we can deploy them at scale.
Oh my gosh, that's amazing. I just can't describe the feeling that I'm having right now, because I think a lot of times we don't realize how beneficial technology like this can be to society as a whole.
That we could go into an environment, rapidly sample it, and try and answer, is the area safe? When I worked at NASA, what took us more than 10 years to do, to collect the training data like we spoke about, this robot team could do autonomously in 15 minutes. So if you look at so many health outcomes like premature births, Alzheimer's, cancers, they have an environmental signature from the physical environment and the social. So we find we can actually learn what they are to then help us make better decisions. Let me show you an example. Low-cost sensors that we can calibrate, that we could then deploy at scale across our neighborhoods, say to measure air quality. Now, why should I care about air quality? Well, the leading cause of poor learning outcomes in schools is absenteeism. The leading cause of absenteeism is asthma. The leading trigger of asthma is poor air quality, and then especially if we strenuously exercise. So the coach, if he or she has kids in their class that have asthma, if they have one of these sensors, they can know, should practice be outside or inside.
Yeah, I actually was thinking that exact same thing, because my son played football, and that's one of the biggest things is the heat and the air quality. And he actually had asthma too. He had a nebulizer for a long time. This definitely would have been helpful to be able to predict when is a good day to.
Yes. Or if now, say I'm a veteran and I have COPD and I want to go and get my shopping. Is it a good time to go? And even which route should I take?
Yeah.
Because the exposure we get on different routes can be orders of magnitude different. To the standardized school testing, it's been shown in many studies across the world that if you take the average test score for a given school, if it's a polluted day, that score across the school will go down. Sometimes any of us have a fuzzy head day.
Yeah.
We don't feel as sharp as we would like. And when that happens, we don't normally think air quality. We're probably not thinking about air quality at all. But, you know, we've all just lived through COVID. We realize that tiny things we can't see that we started wearing masks for can impact us. So actually, it's becoming more and more evident that the air we inhale, when it's polluted, impacts our cognitive performance. And it's particularly true for the smallest particles because they get deepest into our lungs, into our bloodstream, into our brain, where they can cause inflammation. The inflammation influences the delivery of oxygen and then the vitality of those cells. So things like Alzheimer's, which is rapidly increasing, it seems that in part is associated with air pollution causing inflammation, causing the changes in the blood flow, oxygen delivery to the glia and other neurons, which then can have the cognitive degeneration. So it's back to the whole idea the canary doesn't have to die. Is air pollution, impacting our cognitive performance? But it's not just cognitive performance. The World Health Organization estimates, due to pollution, 7 million people die. So more people die in 1 year due to air pollution than happened from COVID over 4 years. And so these are things where we need sensors. For the sensor to be low cost and calibrated, the machine learning can be very, very helpful.
And I wonder, once we deploy those sensors and then look at that data, we can implement things that will help all of us stay healthier and have cleaner air. And, it just is a big deal. I think
the first step is monitoring and knowing what to monitor. It says, what I hope I've shown with these examples is what otherwise would be very intractable problems. Machine learning, by integrating it on multiple levels, can be really useful for a variety of practical applications.
I just thought of a question. I was reading a book, and it was called This Changes Everything. It's about climate change. And one of the things the author talked about in the book was how the world organizations, like you mentioned, set standards for emissions or how much carbon, thresholds that each country gets is supposed to be meeting this, contributing to the world. Is that something of the data that you guys have collected? Is that something that you could share that would help inform the World Health Organizations that are trying to track this kind of thing and see how big of an impact we're making towards climate change?
So there are multiple aspects of that observing system I showed you. For example, we started with satellites. Satellites are really valuable because of the global view for measuring many of these greenhouse gases. And recently, several of those have been also measuring methane at very high resolution. Methane, for example, is about 26 times more effective than carbon dioxide at trapping the sun's energy. So in other words, if these gases are like a blanket on the planet, they're a really thick blanket. Now, the difference from CO2 is its lifetime is shorter. It's about 10 years. So if we reduce the methane emissions, it will have a disproportionate impact quicker than the CO2 will. So yes, these observing systems, from satellites to ground-based aircraft, they are all part of that. Two go hand in glove. They're part of the same system.
Yeah, absolutely. Thank you so much. This is awesome. I think this is really why I say that artificial intelligence is revolutionary, because of the work that you and folks like you are doing on an everyday basis that keeps us healthy, that gives us information that will help us put better systems in place that make us have longevity and create a better earth. And I really appreciate your joining today and giving us the history of how all of this comes together.
Certainly, this was just my small perspective of it.
Yeah. Awesome. Well, thank you so much, Dr. Laurie, for joining us.
Thank you for joining us. This concludes the first episode of our 6-part AI series. We will be learning more about artificial intelligence and providing you with actionable strategies and tools to help you with your businesses and careers. Don't miss episode 2 as we speak with Gregory Richardson about harnessing the power of AI. In episode 3, we'll be discussing the metaverse. You don't want to miss that episode. It's going to be fun. You remember how we talked about Arthur Samuel? Well, Arthur Samuel is also credited with gaming technology. We'll be discussing that and more. Connect with us at currygirltechtalk.com. There you will find videos of our conversation with Dr. Laurie, previews of our upcoming episodes, lists of AI resources are all there, and engage with our AI contest. There you can win an iPad Pro. Just answer the questions and you'll be automatically entered to win. currygirltechtalk.com. As a reminder, episode 2 will be online Thursday, August 8th. Thank you for joining the podcast. I'm Crystal Curry. Take care.